先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第一次 iCANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有
Everyone, welcome to the 183rd talk for iCANX Talks. Today, I'm your moderator. My name is Zhou. I'm from the Material Science Department at Fudan University. And today is the last talk of this month. And we have Professor Yang Lu as the speaker for today's talk. Let me first introduce Professor Lu. Professor Lu is currently a Hong Kong U 100 Scholar Professor in Mechanical Engineering at the University of Hong Kong. He received his bachelor's degree in physics from Nanjing University and a PhD degree in Mechanical Engineering from Rice University and did his postdoc research in the Nanomechanics Lab at MIT. Previously, he worked at City University of Hong Kong as assistant professor, associate professor, and full professor during 2012 to 2021. Professor Lu's research focuses on experimental micro and nanomechanics and its applications in semiconductor and advanced manufacturing. He has published more than 200 articles in leading academic journals, including Science, Nature Nanotechnology, Nature Materials, Nature Communications, and Science Advances. Professor Lu serves as associate editor for the international journal Materials Today, as well as a board member for academic journals such as National Science Review, Journal of China University and Science and Technology, Technology Sciences, and Acta Mechanica Cinena. Professor Lu is a recipient of UGC Early Career Award 2013 and 2014, the NSFC Excellent Young Scientist Fund 2019, and the RGC Research Fellow Scheme at 2020 and 2021. He is an elected member of the Hong Kong Young Academy of Sciences in 2022. With that, I would share my stage to Professor Lu.
Okay, thank you, Joel, for your very kind and detailed introduction. Let me share my screen. Okay, so now it's in the full screen mode, right?
Yes.
Okay, yeah. First of all, I would like to thank Professor Haixia Zhang and the platform of iCANX. And also, my great pleasure and my honor to have so many wonderful guests, panelists here. So I hope that my talk can stimulate some interesting discussion about our research and some related topics. So today, I would like to share our research and some progress on the deep elastic strain engineering of diamond, in particular for their semiconductor and optoelectronics application. So I would just use one slide to introduce my background or my expertise. So my main research field is nanomechanics. This is a very it's a field, and the mechanics we may know that it's with a long history. Right? It's quite a traditional and very important foundation subject for many areas. In here, we focus on the micro and nanoscale because we know that materials behave differently because of the size effect when their critical dimension reduced to the micro and the nano size. In addition to those efforts in simulation and theoretical analysis, we do need experiments, need experimental efforts to tackle these very challenging issues. So we developed some platforms. Actually, they can be date back to my PhD study area when I was in Rice University under the supervision of Professor Jun Lo. So we designed and microfabricated some MEMS kind of device, allows us to perform the very challenging nanomechanical test for the individual nanowires, or later we actually can also extend from the one-dimensional to the two-dimensional. Since I joined the CTU about 12 years ago, I worked with colleagues there to develop some new nanomechanical platforms, including this, we use this DMD platform, like to perform high cyclic fatigue test. I also worked with my former colleague, Professor Shen Yajing, now in Hong Kong UST, to develop some micro robot assisted torsion test platform. So with this expertise and platforms, we were able to study the nanomechanical behavior of materials at the small scale. So this is what my research lab mainly works on. Now, before I move to our main topic of diamond nanomechanics and strain engineering, I would like to introduce two basic concepts, because that's actually very related to what we are doing. So first of all is ultra strength phenomenon. So we know that if you learned some basic material science course, you know that our bulk material, or we say that the engineering materials that we used in our daily life or in our industrial, they can never achieve the theoretical strength. The theoretical strength you can calculate based on the from very fundamental calculations in the solid state physics, or later using some like Frankel's model. They can be around like 1/10 of the Young's modulus, around this value. Or later they can also be derived some other like E over about 3. But we can never achieve that for the bulk materials. There are several reasons, like for metal, there are dislocation, right? Allows the materials can yield and have slip. On the other hand, for many brittle materials, we have fracture. So because of the fracture mechanics, like Griff's criterion, so the materials the ultimate strength of the material will be also limited due to these defects and flaws. So for this reason, so bulk material cannot achieve this high ideal strength. But when the size reduced to the nanoscale, there is a phenomenon called ultra strength. By the definition, is 1/10 of theoretical strength. That's like approaching to the theoretical strength. This can be achieved as shown in many existing results from like the works from the carbon nanotubes, like nanowires, including some of our earlier works. So those works show in here, you can see that by reduce the size to the nanometer scale, it is possible to achieve much higher strength than their bulk counterparts, allowing the materials can reach this so-called ultra strength state. So this ultra strength is not just a mechanics phenomenon. It also has physics meaning. So here I use a plot that I obtained from Wikipedia, showing that how we can get band structure from a crystal. We know that in the materials property, especially the physics and the chemical properties, are highly related with their band structure. But band structure, how they come from? they come from the three-dimensional periodic arrangement of the atoms in the 3D space, so that they form from the each energy level until they form the band structure, right? So therefore, a band structure of the material is highly related with their lattice spacing. That is the average distance of the atoms in the three-dimensional crystals. Therefore, if you applying a mechanical strain to the material, you are changing their lattice parameter. By changing their lattice parameter, the band structure, or we call it the physics behavior, the semiconductor or the electronic behavior will also change upon the strain of the material. Okay, so this concept being actually depicted by Professor Julie and the other colleagues in the field. They call this elastic strain engineering concept, which means that we can apply elastic strain or lattice strain on the crystalline material to considerably change the physical property of material. So this is not an entirely new concept. So in our daily life, we already benefit from this strain engineering concept. Okay, so here I just want to show this the most well-known, most commercially successful example, that is the strain silicon. Strain silicon is actually by epitaxial growth. It's not by applying mechanical strain, but they basically is like you grow single crystalline silicon on the silicon germanium alloy. Because of the slightly larger average lattice parameter, so this heterogeneous growth, the silicon must to have a slightly small lattice tensile strain in order to accommodate the lattice structure of the silicon germanium alloy. Therefore, we have a small amount of the elastic strain in the silicon. But this small amount of the strain can already improve the carrier mobilities in the silicon by 10 times, 100 times already. Okay, so we know that in the device, the electron or hole mobility is the very important parameter which determines the performance of the device. So this strain in the silicon, we call the strain silicon, can effectively boost the performance of the chips and devices. So this strain silicon tech was initially, if I remember correctly, was invented by the IBM. And at that time, very soon that Texas Instrument and some other semiconductor adopted this strain silicon technology. Intel initially did not use this strategy, but later, when they encounter some technological barrier to further extend the Moore's law, they also start to use the strain silicon technology in their CPU and the chips. So this is already a commercially very successful example of the strain engineering. But a few years ago, my research lab actually did some small works on the nanoscale silicon wires. Unlike here, we used epitaxial growth to introduce a small strain. We found that by reducing the silicon wire into the nanometer scale, they actually can be extremely elastic. Okay, as this experiment, this is a real experiment video. So you can see that we really stretch the silicon nanowire like a rubber. They can have very large elastic strain, allows us to have a much bigger strain space to modulate their physics behavior. Therefore, we actually performed some simulation, DFT simulation, to predict silicon band structure upon this large loading. And we found that actually they can have significant band structure modulation. In one of the illustration plot by Professor Julie and his group, they calculate and predict that it is possible to diminish the band gap of silicon. That means make the silicon from a semiconductor to become a conductor, that is metallization. So this is, of course, we have not yet achieved that, but suggests that we have a huge potential by manipulating the elastic strain in the semiconductor to modulate their semiconductor behavior significantly. So that means we have a very good opportunity if we can have an ultra strength material. So by use this ultra strength, we can achieve ultra large strain so that we can manipulate their physical and semiconductor properties, okay, for many unprecedented applications that we can never imagine before. Okay, so back to the main, the actor, okay, the role here is the diamond, okay. So I think the natural diamond is a gem, and we always treasure this very much and consider it extremely expensive. But here I put this image from I borrowed from CNNA, and this is a real picture. It's not a CG animation. It's a diamond ring. Okay, so I guess we should have quite a lot of audience, the female and the girls. You may heard the diamond rings, right? Like engagement rings with a diamond on the top. But now this is a ring that entirely made by diamond. But this diamond is artificial diamond. Okay, so I want to use this figure showing here to illustrate that the diamond may not, as you imagined, you used to think, they're expensive, they are very small, they are very difficult to obtain. But nowadays, the lab-grown diamond, the progress in this lab-grown diamond is very rapid and productive. And we can already grow artificial diamond with much lower cost, much larger sizes, and much higher quality. Okay, so this is one picture we got from a California-based diamond company. It's called Diamond Foundry. But I would like to tell you that, in fact, China, especially Henan, is even called the artificial diamond capital. We actually produced most of the HPHT diamonds for industrial application to provide towards the overall world. Okay, so but that diamond is mainly for serve as the mechanical application, just as shown here. Okay, so because I think I don't need to explain too much about the property of diamond as the hardest material in nature. Okay, but this artificial diamond, they can be used in the drilling, right, in the cutting, in the polishing, grinding. Okay, so this is a photo that we used for the Chang'e. Actually, they also using a diamond tool to dig those ground and the materials from the lunar Earth. And actually, there are a lot of exciting progress in the recent years that scientists continues to explore the innovative structure, microstructure to achieve even higher hardness or even higher toughness of the diamond compared to the natural diamond. Some example including like nano twin diamond or nanocrystalline diamond structure. As those diamond can be even have a higher hardness or toughness that can better satisfy the needs for us to have like a fine machining, high precision cutting, or advanced manufacturing. But I want to show another phase of the diamond as a Mountain Everest of electronic material. Okay, so besides as the hardest industrial material, diamond is actually an ultra wide band gap semiconductor. It has a wide band gap up to 5.3 or 5.4 eV, which is extremely large. So probably in the past, in some of the high school textbook may describe diamond as the insulator, but I would like to let you know this is actually an ultra wide band gap semiconductor. Especially nowadays, wide band gap semiconductors are so important, right? Used in the EV cars or in the 5G, okay, power electronics. So diamond is very ideal wide band gap semiconductor. Also because it has a highest thermal conductivity. So I may not show this animation here, but you can search online. If you want to cut a piece of an ice block, it's very difficult that you use normal knife to cut the ice. But if you have a piece of a diamond, you can actually cut with your finger. When you hold your finger with the diamond piece to cut ice, you can cut the ice just like you cut a bean curd. Because diamond can quickly, transport your heat from your hand, from your finger to the material because of its almost highest thermal conductivity compared to any other material, okay? Also, because of its ultra wide band gap nature, it has very high dielectric breakdown strength, allows the diamond are very suitable for the high power, high frequency application. In fact, diamond also has a very high carrier mobility. Of course, I'll also mention that we need to have the carrier in the diamond first, right? So it's such a wonderful ideal semiconductor material. Even the defects in the diamond, it's also amazing. We have several friends and colleagues in the community working on quantum science. In the quantum information technology, there is a special defects in the diamond called the NV center. N is a nitrogen and V is vacancy. So if you have a pair of a nitrogen in the diamond and with a vacancy beside, you can have a very unique quantum defects. And this so-called color center can provide a lot of the interesting quantum sensing, quantum mechanical behavior. Okay, so therefore, because of these amazing properties in the research field, there are already many efforts and investigation on using diamond for like integrated circuits, the device or the field emission transistor, diamond-based transistor, or based on the diamond photonics structure, and also to couple the quantum and nanomechanical behavior to form a high quality resonator as the sensor. So I may not be able to cover this content here, but if you are interested, I do recommend you to explore the functional application of diamond. Okay, we did write some review if you're also interested. But let's back to the semiconductor side of the diamond. Okay, so now we are in the 5G, right? In the 5G time, and in the future we will very soon to face the opportunity of the 6G and other high frequency information technology. On the other hand, the popularity of the EV, right, electrical vehicles, and also a lot of the electrical like flying machine and also boat, right, electrical boat requires a lot of the power electronics devices, and in this near future or future application, diamond is a very good candidate for those high power, high frequency applications. The reason I'm listed here, you can see that these properties, including band gap, breakdown strength, electron mobility, and thermal conductivity, you can see that diamond is not only better than this silicon, but it's also better than the very popular nowadays so-called third generation semiconductor. Okay, the silicon carbide and gallium nitride, they are the two wide band gap semiconductor, but you can see that diamond compared to these two, it has higher band gap, much higher breaking down strength, and much better thermal conductivity. And even they have higher electromobility compared to these two and also silicon. Of course, you have to ensure that you have the electromobility carrier first. So these are very fascinating properties make the diamond really a very ultimate semiconductor for those future application. So you can see it has a much better power handling ability and have much better power operation frequency. So there are some media and to even describe diamond could be the future semiconductor material beyond the silicon age. As we now know that for the silicon-based electronics are facing to its theoretical limit, right? So to continue extend the Moore's law, researchers are exploring a lot of the other new materials. Besides those third generation semiconductor, they're also based on like a carbon nanotube or two-dimensional materials. But some researchers consider diamond may also have a very good chance to moving beyond the silicon. But the reality is that we also recognize that diamond also have some some challenge we need to overcome. One of the big challenge is that the doping. We know that we never use intrinsic silicon for the transistor, right? For the chips, but we use p-doped or n-doped silicon. And now the doping of the diamond, if you compare to the data of the silicon, is very challenging. Imagine that although they have same diamond cubic crystalline structure, but the diamond has much smaller lattice distance, means that they have tighter crystal space. The atom, the carbon, right? Diamond is based on the carbon. It has a much smaller the atomic number compared to silicon. That also means it have limited doper. Also, even if you can dope some of the material, often they result some so we call the deep doping. So it's not a shallow doping, it's a deep dope. It's because of the large band gap. So that makes the doping of the diamond remains a challenge. Researchers make some very nice progress in the p-type dope, but for the n-type dope, there are still some problems. So which we need to overcome. And actually, our research group recently did some of the theoretical works. We try to address this the deep doping issue in the n-type doping. Now, let's think in another way. We mentioned that in the very beginning that when we reduce the material into the micro and nanoscale, it is possible that we can achieve ultra-strength state. With ultra-strength state, we can use strain engineering to modulate the material's behavior. Okay, so as depicted in this MRS bulletin review paper by the Professor Julie and other colleagues, so we can imagine that if we can have a large deformation state in the diamond, then we might be use elastic strain engineering method to modulate diamond's band gap structure. Okay, so it is easy to imagine, but in reality, if you want to deform or if we want to strain diamond, here is a video. Okay, I borrow from YouTube. I don't have sufficient fund to allow us to perform such an expensive experiment. But you can see that if we want to deform a bulk diamond, instead of being deformed elastically, it usually fractured in a catastrophic way. So that means we cannot deform or strain bulk diamond. However, if we reduced diamond geometry into the nanoscale, we found that, surprisingly, that diamond become quite flexible. So this is on the left-hand side, is an experiment that we achieved about, I think about nearly 10 years ago. At that time, when my postdoc and my student performed the experiment, and they found that initially we want to perform a diamond nano indentation test, but we found that instead of the indentation, our indenter has been was fractured by the bottom diamond nanoneedle. So this diamond nanoneedle is made by the etching of the diamond film. My collaborator, Professor Wenjun Zhang, and his research team, they are expert in make a diamond film. And by etching this film, they can obtain some of these, we call the diamond needle structure. And this is a very ideal sample to allow us to investigate their nanomechanical behavior. And through this experiment, we found that when the size was reduced into the nanoscale, actually diamond needle can be bent elastically. That means if you withdraw your nano indenter, they can be fully recovered. Okay, so this is a first experiment and first video showing that nanoscale diamond can be very elastic. Remember that our experiment is quantitative. This nano indenter still records the force and displacement, and also together with this force and the displacement data, we also perform this finite element simulation to couple this experiment. We can also find that this diamond has reached ultra strength state. You can see that upon this bending, there's quite a significant fraction of the sample are under very large strain. Actually, by perform 1-to-1 simulation, we found the largest elastic strain is already more than 8%. This is a huge value. Okay, imagine that the bulk diamond is almost considered as impossible to be deformed. Okay, and also the corresponding strength is about 89 to 98 gigapascal, also approaching to the theoretical calculation of the diamond strength. Actually, one of our collaborators, Professor Feng Ding, and their team developed an MD-DFT simulation and suggesting that the theoretical elastic strain of the diamond is about 13.5 or 8, about 13%. So our result, about 8%, is already quite close to the theoretical elastic strain. The strength is also close to the ideal strength. That means we can achieve ultra strength in nanoscale diamond. So this work actually stimulates a lot of interest. Okay, I think it may change the people's impression about diamond, because diamond usually is considered is the most hardest material and can be never been deformed, but we show that it can be indeed elastic. So my postdoc, the first author of that paper, is currently an associate professor in Kyoto University, and the co-first author, Dr. Hongti Zhang, is now a professor in the Shanghai Tech University. So this is a very interesting work. Not only it shows that we can achieve extreme mechanical behavior of diamond in the nanoscale, but also open up new avenues, suggest that we can explore the new physical properties of diamond when they can be so elastically stretched. Okay, so there are, I show some of work by the MIT group, and also the Jilin University and Nevada University. They perform some calculation, because now in the past, people may not imagine that we can achieve such a large strain in diamond. But now, since the experiment suggests we can indeed achieve large strain in the diamond, so we can indeed predict what kind of the band gap of the diamond upon this large strain. Okay, so therefore, news from MIT website, it's an independent work, but they comment our works on the diamond and the silicon, showing that by achieve these ultra strengths, they open up new avenues to develop, to explore how device can be designed and fabricated based on these more dramatic changes in the material's property at a nanoscale. But as an engineer, okay, we are not very satisfied by this configuration. So in our past experiment, you can see that the diamond sample was by randomly etched. So their geometry is irregular and cannot be well controlled. Also, this loading at that time is a compromised configuration, because we can only use a sideways face of the indenture to bend. But you know that the bending usually creates a gradient strain distribution, right? So it's not a uniform strain. So if we want to take advantage of the strain, the large strain for the device application, we want to have a more uniform strain in the diamond. Of course, for device, we also want to control the geometry of the diamond. So therefore, so this is a more familiar configuration for mechanical engineer. So we all know that the tensile loading or tensile specimen is the most straightforward configuration to perform not only mechanical test, but is also most ideal for conduct strain engineering, because uniaxial tensile can provide the more uniform elastic strain. To achieve that, we need to ensure we can obtain the well-controlled micro device of the diamond. So therefore, in this work, we collaborate with a team from Harbin Institute of Technology, by Dr. Bing Dai and Professor Jiaqi Zhu and Professor Jiecai Han's group. So they have a skill to grow single crystalline diamond in large pieces. And also they can control the orientation of this single crystalline bulk diamond. So with this high quality single crystalline diamond, we developed a microfabrication technique to microfabricate the micro bridge of the diamond. Okay, so this is a micron scale sample, but with the critical dimension in the center, we call the gauge section, with a nanometer scale. That is about like 200 nanometer width and 200 nanometer in the thickness. Therefore, this micro bridge of diamond is a very ideal sample and a platform, allow us to conduct the desired strain engineering work. Okay, of course, we also need to microfabricate many samples and also the grips that can robust enough to test this diamond. And also this time we perform all the tests in the TEM because the TEM allow not only provide the higher magnification, but also allows us to examine the crystalline structure and the surface morphology, as well as the fracture morphology in situ. That means in real time, we can observe the deformation, the microstructure, and to examine their deformation is elastic or plastic. Okay, so based on this platform, actually in the metal community, the researcher in the Berkeley lab, they already use this configuration to study the size effect of the metal. And we adopt this kind of method to perform the tensile test of the diamond. Okay, so here is the video I want to show in our tonight's I think a presentation. This is probably the most important video that I want to show. So pay attention, this is our sample. This is the micro bridge, the gauge section of the diamond. And we also have two markers here. So you can easily to see that through the microfabrication, this micro bridge of the diamond can be elastically stretched. Okay, so this stretchability is so significant that you can, just by naked eye, you can already see that it's being significantly, substantially deformed. And every time when you unload, the material is fully recoverable. So that means the diamond not only become more flexible, but they can have much larger tensile elasticity. So by checking this one by one, frame by frame, we can show that in this particular sample, we can achieve a maximal 7.5 elastic strain, which means upon unload, this 7.5 elastic strain can be fully recovered. But I want to point out that this 7.5 strain is the whole piece of the sample in the uniform state, rather than in the bending diamond, which the strain is only localized in a small area. And actually, if you analyze the two areas close to the gripping part, the local maximal strength is already more than 9%. That is already higher than our last paper. So with such a large uniform tensile elasticity, we are very excited at that time when we achieved this result, but we can find that we still have room to improve. So later, we further optimize the geometry of this micro bridge to reduce the local stress concentration. We eventually can approach nearly 10% elastic strain in this sample. So if you remember, we showed that theoretically, the maximal elastic strain can achieved in diamond crystal is about 13%. So 10% is not only the ultra strength, it's we call the deep ultra strength. That means it's more than half of the theoretical strength, means really approach the theoretical strength. So our experiment is highly repeatable, and we found that it's consistent that we can achieve such a ultra large uniform tensile elastic strain in all the orientation 111, 101, 100. Okay, so at that time, we only summarized some of the very best results in the 101, but in our recent experiment, we shows that for the 100 and 111, they can also achieve almost like 7 or 8% of the elastic strain. So this is a huge number, okay? So if I put the bulk diamond, it's probably here. I just even here is already exaggerated because almost there's no deformation for bulk diamond. But for the nanoscale diamond bridge, even by microfabrication, we can achieve near ideal strength. Okay, so now we can achieve this uniform tensile strength. How can we use this for the strain engineering? Okay, first of all, we perform the DFT calculation. So in the DFT calculation, okay, this is diamond primitive cells, a Brilliant zoom. Brilliant zoom suggests that we can actually compute along each direction 100, 101, and 111 orientation. And in this calculation, we simulate, just like in our experiment, we load the sample uniactually along the 100, 101, and 111 orientation. So this is the real space, this is the reciprocal space, and this is the corresponding band gap evolution. And you can see that along all these three directions, okay, the band gap always reduce. So this is good because just like I said, normally people consider the ultra wide band gap semiconductor diamond as the insulator, but by stretching the diamond, their band gap reduce and the more and more close to the normal semiconductor. Okay, and also we observe that around 9% of the tensile strength along 111 orientation, the conduction band minimum may switch from this point to this point. That makes the diamond become a direct band gap semiconductor. So we summarize this result here. Okay, so we see that along the 101, they have the largest reduction rate, making the diamond from a 5.1 EV to become a 3 EV. That is similar to the third generation band gap semiconductor like silicon carbide, gallium nitride. So we can anticipate that they can be very useful for this wide band gap semiconductor application. But more interesting is that at 9% strain along the 111 orientation, it will become a direct band gap semiconductor. That opens up opportunities for optoelectronics. So you can see this elastic strain engineering is not just like before in the strain silicon, they changed the carrier mobility. But now we see that they have some fundamental changes, like from insulator to become a wideband semiconductor, from an indirect band gap semiconductor to become a direct band gap semiconductor. So this is some fundamental change. It's not trivial, okay? So therefore, we think our deep strength can provide a deep elastic strain engineering. Okay, so we not only calculate this trend, but we also verified this prediction by experiment. Okay, so in this experiment, we collaborate with Dr. Yang, now is in PSU, and Professor Andy Miner in Lawrence Berkeley National Lab. So in this experiment, we used a predeformed diamond sample, and through the predeformation, we can have a strain distribution. And this strain, we can know that like in the A area is almost a strain-free state, and in the area near the crack tips, we have they have tensile strain distribution, and we can also confirm that the area of the C has the higher strain than the B. And from that, we use the EOS measurement. EOS actually is an energy loss spectrum. So they can help us to measure the local band structure, band gap of the material. And you can confirm that in the stress-free area, the band gap is about the intrinsic diamond, that is about 5.3 EV. But upon the tensile strength area, the band gap reduced to 4.3, and with a larger elastic strain, the band gap reduced to 3.6 EV. So that is quite consistent, or we can say agree very well with our prediction, okay, in the reduction of the band gap upon the increased strain. So this confirms that indeed we can use the strand diamond for the device. Okay, so therefore, we propose that in the future, we probably can design the micro device of the diamond with a larger string being introduced so that they can be useful semiconductor device. To confirm that, we actually performed some scale-up microfabrication to show that we can indeed fabricate like the arrays of the diamond. We call the like this in the 3 bridge, okay? And you can see from the experiment video that this micro bridge of the diamond can be indeed stretched elastically, like, okay? And of course, this is just a simple illustration, but suggests that this microfabrication can be scaled up, okay? So we can have the 3x3, okay, or even more complicated 2-dimensional arrays of the diamond micro structure. Actually, currently in our group, we have a student working on that and making more complicated 2-dimensional arrays of the diamond, or even in the future can be possibly in the 3-dimensional. Okay, so I don't want to repeat this summary. If you are interested, you can take a look at our latest paper published 2 years ago. And lastly, I want to offer some of the insights. Okay, so our expertise in the nanomechanics is not just some measure some mechanical properties of the materials, but our results suggest that in the nanomechanics study, we can discover some new opportunity, like the extreme mechanical properties we shown here in the nanoscale diamond. This extreme mechanical property can actually brings us the new semiconductor opportunity. Okay, so some of the physics are very excited about our research, and they believe that by demonstrating this level of larger strain in the diamond, we can open up many possibilities, okay, in the semiconductor and in the optoelectronics. So we also very glad to see that more and more researchers and experts in the physics and optoelectronics are joining this exploration. Okay, so we see that researchers further calculate, okay, if it is actually possible to achieve metallization of the diamond in a large deformation state. Okay, and also there are researchers from Jilin University. They suggest that if we can combine the compression and the shear deformation, it is possible to achieve the intrinsic superconductivity in the diamond. Okay, so of course these are still in the simulation stage, but at least our experiment already suggests that it is possible to achieve this larger strain state. Okay, we're also very lucky, very happy to see that Professor Yang Wei and Professor Tianyong Jun, they achieve almost the theoretical limit of the elastic strain in the diamond when they microfabricate a very sharp diamond needle and also polish the surface very smoothly upon the atomic smooth. It is possible to achieve this certain percentage. So as I said, it's almost a theoretical limit. Okay, so that means this study can continue and we can explore more the exciting phenomenon and the physical properties by extreme the mechanics of the diamond. So currently in our lab, we are trying to really investigate the mechanical and the optoelectronic coupling of the semiconductor materials, including diamond, upon this deep strain. There are some setups we already built, which is still in the very preliminary stage, that allows us to stretch the materials. Meanwhile, we use a C-air detector, cathodoluminescence detector, to detect the emitted light wavelengths allows us to analyze the band structure of the diamond or other semiconductor. So we already achieved some interesting result in the gallium nitride, but because of the time, I'm not going to go deep here. So therefore, we believe that if we can tackle all the challenges, solve all the problems in the diamond, including doping, we may able to see a new age of diamond that is we can really use in diamond for the future electronics. And I want to also mention that one of the first author of our team, Dr. Chaojun Dang, who currently joined the Zhejiang University, got MIT TR 35 China. So I would like to say we're glad that many peers and the community recognize our efforts in this regard. And lastly, I want to point out that not only for diamond, okay, this strain engineering concept can extend to the two-dimensional crystal. So I think for the two-dimensional crystal, mostly familiar is a graphene, right? So in our another work, we demonstrate that we can experimentally achieve very large elastic strain in freestanding monolayer single crystal graphene. Okay, so this is not a mechanical measurement, but also showing that we can actually perform strain engineering of two-dimensional material. Okay, so the two-dimensional material nowadays not just like a monolayer material, they can be homostructure and it can be heterostructure. Okay, and the graphene itself may not be a semiconductor, but we know that the graphene nanoribbon, right, is a semiconductor material. And also there are some other two-dimensional semiconductor like molybdenum disulfide. By applying this larger strain, elastic strain, we can anticipate that these can also fundamentally change the physical and the semiconductor behavior of 2D crystal. And for their heterostructure, okay, so now a very hot topic in the two-dimensional crystal field is the twist bilayer graphene. So researcher in MIT found that actually by stacking two graphene with a small angle 1.1, they call it magic angle, right? So they can achieve like a superconductivity, right? This is already being recognized by the Wolf Prize. But now, if we can stretch twist bilayer graphene, what will happen? So that is some open question that I believe that many of our audience can think, because we are for the twisted bilayer graphene is change the periodicity, right? But by applying a strain, they can also change the asymmetry. So this can also coupled and have some new properties. So therefore, one of my students already achieved the straining of twist bilayer graphene. And we also want to investigate whether this can bring some new semiconductor device opportunity. So that is the concept we call can couple the twisttronics with the stretchtronics, couple the twisting and the stretching. They may offer some new opportunities. So that's some our insights. And lastly, I want to say mechanics is very broad, okay? And not only elasticity, actually plasticity can also give us a lot of interesting behavior. Okay, so the last year we published a work with collaborator showing that all inorganic perovskites can be plastically deformed, and not only they can be substantially deformed, they may also form some interesting geometry. Okay, so this plastic deformation is not only interesting mechanical behavior, but also allows us to design some interesting deformable electronics, or we can microfabricate some special device based on this deformable semiconductors. So that is another area I hope that I have an opportunity to share with you in the future. So the ductile semiconductor is another growing area in this area. So I would like to finish here, and I would say we really believe that there's many opportunities in the nanomechanics, and by combining the nanomechanics and the semiconductor material, we will see a lot of new applications. And I hope that our talk can be interesting and stimulating some interesting discussion. Okay, so yeah, the chair, I finish here.
All right. Thank you, Professor Lu. I think this is a very interesting topic, that by deep stranding these semiconductors and 2D materials, we can find many new opportunities for these materials. And actually, with this interesting topic, it is also my pleasure to announce that we have the largest number of panelists in iCANX history today. So before our discussion, I would like to introduce our panelists one by one. Our first panelist is Professor Jingchi Han, who is an assistant professor and Boya Yang Scholar in School of Integrated Circuits in Peking University. And he received his bachelor's degree and master's degree from Tsinghua University in 2013 and 2015, respectively, both in electrical engineering. He received his master's degree and PhD degree from MIT in 2018 and 2021, respectively, both in electrical engineering and computer science. Prior to joining Peking University, he was a postdoc associate in research laboratory of electronics at MIT from 2021 to 2023. His research focused on new paradigms of active micro and nanostructures for applications in sensing, actuation, computing, storage, and energy harvesting, aiming to reduce the energy consumption of key components of microsystems and promote their applications in the fields of the Internet of Things, artificial intelligence, wearable electronics, etc. His innovative work on nanoelectronic mechanical switches, active acoustic metasurfaces, and piezoelectric transducers and magnetic electric transducers have received extensive media coverage and attention from the industry. He has published over 20 peer-reviewed articles and co-invented 5 patents. And our second panelist is Professor Zhengbao Yang from Hong Kong University of Science and Technology. Dr. Yang received his bachelor's degree from the Harbin Institute of Technology and his PhD degree from the University of Toronto in 2016. He is now an associate professor at the Hong Kong University of Science and Technology, affiliated with the Department of Mechanical and Aerospace Engineering. He has applied for 24 patents in China and in the USA, and authored over 120 academic articles in high-impact journals such as Nature, Nature Communications, Science Robotics, Science Advances, Joule, etc. Dr. Yang is an IEEE senior member and has been listed as one of the top 2 scientists in the world by Stanford University. His research interests are vibration and mechatronics, with a special focus on developing smart structures and dynamic systems for energy harvesters, sensors, and actuators. This interdisciplinary research area requires combining knowledge and skills in mechanical design, electrical circuits, and smart materials and dynamic analysis. Our third panelist is Professor Qin-Song Xu from the University of Macau. And Professor Xu is with the Department of Electromechanical Engineering, Faculty of Science and Technology, University of Macau, and Director of the Smart and Micro Nanosystems Laboratory. His research involves intelligent micro nanosystems, precision robotics, and biomechanical applications. As the principal investigator, he has been granted over 20 projects, including key projects of the Macau Science and Technology Fund. He has published 4 books and over 380 papers in the international journals and conferences, cited over 12,000 times in Google Scholar with an H index of 63. Professor Xu has received more than 10 Best Paper Awards from international conferences and multiple times of Macau Science and Technology Awards from Macau SAR, China. He has been selected into the top 2% of the world's top scientists released by Stanford University since 2019. He currently serves as an associate editor of IEEE TRO and the IEEE TASE. He was a technical editor of IEEE ASME TMAC and the associate editor of IEEE RAL. He is an editorial board member of Chinese Journal of Mechanical Engineering. He is a fellow of ASME. Our fourth panelist is Professor Su Juanli. She is a professor and a PhD supervisor, and also serves as the dean of the School of Mechanical and Precision Instrument Engineering at the Xi'an University of Technology. She is among the inaugural members of the National University Huang Danian style teacher team and is recognized as a leading figure in teaching under the Sanqing Talent Special Support Program and as a teaching master in Shanxi Province. In 1990, she obtained her bachelor's degree in mechanical design and manufacturing from Shanxi Institute of Mechanical Engineering. She later pursued her master and PhD degrees in mechanical manufacturing and automation from Xi'an University of Technology in 2000 and 2006, respectively. From 2009 and 2011, she conducted visiting research at Missouri University of Science and Technology in the United States. She has dedicated her career to the research of ultra-precision machining of hard and brittle materials. Her innovative contributions include studies on high-speed ultrasonic cutting mechanisms and parameter control of large diamond ultra-thin silicon carbide single crystal wafers, the micro-cutting mechanism, and the parameter control of silicon carbide single crystal using strong plasma ultrasonic, as well as the mechanism and critical conditions of plasticity brittle transition in silicon carbide single crystals. Her work has garnered widespread attention and media coverage within the industry, with over 130 academic papers published, including more than 80 indexed by CI and EI. She has authored 4 books and holds 13 granted invention patents. She has led 2 National Natural Science Foundation projects, 1 key and major project each from the Shanxi Provincial National Science Foundation, and 2 projects from the Shanxi Provincial Science and Technology Research Program, and 3 general projects from the Sanxi Provincial Natural Science Foundation. She has been recognized with several prestigious awards, including the first prize for the excellent scientific and technological research achievements in Sanxi higher educational institutions, 1 second prize for science and technology in Sanxi province, and 1 second prize for science and technology in higher education institutions in Sanxi province, and 1 third prize for technological progress in Xi'an City, and 1 second prize for technological progress from the State Administration of Machinery Industry. And our 5th panelist is Professor Jun Liu from the City University of Hong Kong. So Professor Liu is an assistant professor in the Department of Mechanical Engineering at the City University of Hong Kong. He obtained his PhD from the University of Toronto in 2016 and his bachelor's degree in automation as well as in economics from Sandhurst University in 2008. Before joining CTU, he worked at the Dalio Institute of Cardiovascular Imaging at Weill Cornell Medical College, where he conducted research in advanced medical imaging technologies. His pioneer research has been recognized at the flagship robotics and automation conferences by winning multiple awards, including the Best Student Paper Award, Best Medical Robotic Paper Finalist Award from the IEEE International Conference on Robotics and Automation in 2014, and the Galtech Best Paper in Robotics Award from the IEEE International Conference on Information and Automation in 2016. And our 6th panelist is Professor Long Yi from the Chinese Universities of Hong Kong. Professor Long graduated from the University of Cambridge. She is the Fellow of Royal Society of Chemistry and professor in the Chinese University of Hong Kong. Her research focuses on smart materials and devices. Her career started with successful lab-to-fab technology transfer to industries, including Seagate Technology. Her recent work won Falling Walls Science Breakthroughs of the Year 2022, top 3 of the Green Awards in the energy category of the Green Awards in Berlin 2022, Tech Connect Innovation Award in Washington 2016. Her research activity was highlighted in Nature and was reported by Reuters, AFP, CNA, MIT Technology Review, and many others. So with that, let's start our discussion for today. So who would like to ask the first questions?
Yeah, maybe I start first.
Yeah, please.
Hi, Yang. It's the first time I heard about your second work about how to integrate with the elasticity with the electronic properties. It's fantastic. Actually, I think this is really something very new here, I think. So my question here is because I used to work in semiconductor. So we know how difficult to fabricate IC. And, you know, if you want put the string there, it's not easy at all, right? You have to put epitaxial growth successfully without defects here and there. So I think this is a quite difficult hurdle for whatever diamond technology into the real IC or the chips. And maybe for the like a flexible one, it's easier, but for diamond, I think it's quite difficult for diamond to put on a soft electronics, right? So that's why maybe perovskite or there's a soft thing is doable. So can you just share your insight on the integration of the string technology with the real semiconductor fabrication? Thank you.
Okay, thank you, Professor Long. You are the expert in the semiconductor manufacturing. Yeah, we worked on some fundamental study, right? And we illustrate that theoretically it is possible, at least it's possible to be elastically strained. But indeed, there are technological challenges that we need to overcome. We do think, and actually we tried some method to fix the strain. It's definitely unlike the epitaxial growth, which is almost like a very stable, right? Stable and permanent. But we can indeed fix the strain by design some mechanical structure and also use some techniques. So one example, I think we know that in Chinese construction design architecture, we have a 榫卯结构, right? 榫卯结构. So that means we can design some structure that use the material itself to fix the deformation of some part of the diamond, so that they can support some part are under the strain state without using like glue. So that's something that we are working on and trying to fix the strain in the diamond structure for a real device. Of course, if you want to scale up, to have an industrial level to larger scale to fix the strain, it's challenging, but we can start with some small strain, not necessarily like this ultra large strain. With a smaller strain, there are still way to fix. So of course, that's just some of my own comments, but we look for expert in the semiconductor manufacturer trying to address to this challenge.
So 10% you can reduce from 5.5 to 3, 10% strain, right?
9% can already reduce to about 3.5, 3.3. Yeah.
Yeah, cool. Yeah, we can discuss offline. Thank you. It's a great work.
Sure,
Yeah, it's first time I heard about this. It's definitely, I think it's a huge breakthrough. Yeah. Thank you.
Yeah, who is going to ask the next question?
I can ask. I like to.
Okay.
Thank you. I think to Dr. Zhang have me to join this high level talks, and I think Dr. Lu shared a fabulous speech. In China recently, we called that electrical vehicle is very popular in China recent years, and just most electrical chip it's power inventor use that chip called usually use IGBT. The chip is made of silicon carbide. And you share this fabulous work. I think probably you see the physical properties of the diamond much better than silicon carbide, even other semiconductors. So just one question, I think, do you think compare of this power inventor, maybe this diamond chip much better than silicon carbide chip? So what's your opinion?
Yeah, thank you, Professor Lee. It's a very good point. So yeah, EV is a very important field, and it's actually the main economy driver right nowadays in China. So currently we see that many of the power electronics in the EV use silicon carbide, right? And we did show that the diamond, in principle, they have even better figures of merits compared to silicon carbide. But as I said, there are still some challenge to really use that in the real industrial, including some of the like doping and some other microfabrication, and of course, cost maybe also at the moment is still a concern. But I want to say that the power electronics is one of the direction that the diamond semiconductor can aim for. So it's definitely the direction, one of the important directions we need to pursue. On the other hand, diamond can be immediately used in the power electronics right now, but not as the semiconductor itself, but use their ultra high thermal conductivity. So currently, there are several researchers, and including actually one of my research team in my group. So they are actually exploring to couple the diamond with the silicon carbide and the gallium nitride to boost the performance of the third generation semiconductor. So it can be already used, because for this thermal management application, we don't need this electronic grade diamond, but we can use in thermal grade diamond. So that price is acceptable. So this is some immediate application they can already contribute to the EV development. Of course, the long run, in the long run, we still wish to use the diamond for the next generation power electronics. That's why some in the industry or in the business world, they call the diamond as the third or the fourth generation semiconductor. So that's the future. But we can already immediately use the diamond for the current third generation wide bandgap semiconductor already. Thank you.
Okay, thank you. Thank you. We look forward to the fourth, generation of the, popular chip of diamond. So thank you. Thank you very much.
Thank you.
Yeah, it seems like there are many different opportunities for this new technology. Okay, who is going to raise the next question?
Hi, let me ask a question.
Please.
Okay.
Okay, Professor Xu. Yeah.
Me. Okay. Thank you. Thank Professor Lu. Okay, thank you very much for your insightful presentation and research. Yeah, your research is very widely covering semiconductor and also different kind of material. My research is about micro robotics, micro nano robotics, manipulation, automation. So I think your research has inspired me for future research, maybe how to combine the diamond, with the micro robotics for different kind of applications. Okay, I have a question for your presentation and maybe for your research. I know you have published many papers on science, right? And very insightful work can be published here. Okay, here, and can you share maybe give some introduction, share your experience how to publish paper in science. Okay. Thank you.
Thank you. That's I did not publish many, just a few. Yeah, I would like to say, first of all, I agree with you that diamond can be also an interesting material to explore for this micro robot and micro mechanical device. So there are already some study, I think, from Japan and in Europe, some of the diamond-based MEMS device. So they can microfabricate a diamond as a small gear. So they have a very nice, the mechanical property, like including friction and lubricity and anti-oxidization issue. So it's actually a very nice material for the micro machine and the micro robots. So that's indeed a interesting direction that you may take a look. Yeah. Okay. So yeah, to publish paper in some multidisciplinary journal, of course, is nice because it can stimulate other researchers from many different fields explore this diamond as a new material. Yeah, actually, it's also not a very easy way for us because we mainly work on mechanics. As I said in the beginning, it's a very traditional subject, right? And it's an older but a very important field. So it's always a challenge even for ourselves. But I think maybe if here there are some good experience is that we work on the interdisciplinary research that we combine the mechanics with semiconductor. I think this is some of the new direction or the cutting edge, the frontier in the field, so that some people may not imagine before how mechanical loading or mechanics can drive the physical or semiconductor property change or applications. So I think the interdisciplinary research is always a good direction that can stimulate interest. And also through this process, we can also work with many outstanding collaborators. So I mentioned in my slides, we do have many material scientists, chemists who can grow nice material. We also can work with physicists to understand the underlying physics. And the electrical engineer can offer some insights for future development. So through that process, I benefited from many collaborators in my former university, CTU, and from Harbin Institute, from MIT, international collaborator, from IBM. So that's actually a very rewarding process.
Okay, thank you much for your sharing. Yeah, multidisciplinary is very important, right? Okay, thank you very much.
Yeah. Thank you.
Thank you.
Okay, Professor Yang, I think you just
Yes, thank you. Thank you.
yeah.
Actually, thank you, Professor Xu. You asked me the same question. I want to ask the same question. So I have another question for our dear Professor Lu. I work on ceramics. Ceramics is not as pure as a diamond. Diamond is very pure or beautiful. So I was thinking when you're doing the wonderful inspiring lecture, is that possible we can use a similar method to study, to test polycrystalline solids? Thank you.
Okay. Yeah, I know that you are an expert in the piezoelectric material, right? And use this for the device and yeah, you publish. I read many of your papers published in the top journals. Yeah, I think the piezo material crystal is actually a very nice, very ideal sample for this kind of research, like what we're doing, coupled mechanics and electricity, right? Or electrical behavior. So I have not yet tried, but I may imagine that for the piezo ceramics, they might be some interesting nanoscale mechanical behavior. And with that, if we can measure the in situ, so probably we will find some interesting piezoelectric behavior. So that is something, yeah, we should definitely think about. But yeah, but not yet. We have not yet tried. Yeah. So maybe we can discuss in the future.
Great, thank you. Thank you. I'll listen for you. I will go check you. Thank you.
Hi, Professor Lu. Thanks very much for your great talk. Yeah. Actually, I have a question like about. I'm very interested in like using the string engineering to tune the bands of like band gap of the diamond. I'm just wondering like when you tune the band gap to like something similar to like gallium nitride or silicon carbide, like what could be the biggest advantage over these kind of traditional like compound semiconductors? Can you comment on that?
Yeah, thank you, Professor Han. Yeah, strain engineering is, or we call it strain, elastic strain engineering is unique is because it's a dynamic process and it's a reversible process. That means we can modulate, we can tune the band gap continuously or reversibly. So we can convert from diamond from deep UV, right, and towards a blue, purple light continuously. So this is like a traditional strain engineering, like by epitaxial growth, you cannot achieve this continuous modulation. So this is a first thing that our mechanical method, mechanical strain can bring. And secondly is our strain is not just some small strain. I think if just introduce a small strain in the material, in the nanomaterial, I think many other people are also working on that, and we can also see some results from like strain engineering of 2D materials, right? But that is can be expected. But in our strain, it's a deep strain. It's something that people may not imagine or may not expect before. So under such a large strain, the physical property change is revolutionary. Is some substantial fundamental change, like the indirect band gap to direct band gap. But this kind of change is unique and cannot be easily achieved in some of the other method or other tuning strategy. So we believe there might be some opportunity here, but in any sense, so such a large strain can be only achieved by mechanically. So it's not easy to be introduced by some other method. So there are some advantage and disadvantage because of course, one of the disadvantages is how to for such a very large strain, how to fix it, right? How to make it stable.
Yeah.
Yeah.
Okay.
So that's
Thank you very much.
My 2 cents. Yeah.
Yeah. Thanks.
The flexible electronics may have something, but the problem is all these ceramics, right? So it's kind of difficult to integrate with any soft substrate. So yeah, so on one hand, it's 10%, 9% is quite difficult by normal epitaxial growth, you know. But anyway,
right.
so just
yeah,
just fundamental science study. So yeah, so
yeah. But I want to also point out, like the earlier I showed the silicon nanowire case. That strain is really huge, like more than 10%, can even up to 15%. So if that nanowire is by VLS growth. So by VLS growth, we can consistently achieve those nanostructure, nanowire of the materials, and they can have very large strain. So they may have application in flexible electronics. Because in the past, like I remember I heard some talk about flexible electronics, people saying, okay, so semiconductor is cannot be elastic, cannot be flexible, so we need a polymer, we need those PDMS, some other material to have the elasticity. But you can see here actually silicon can be quite flexible. So I also read some works by our peer like Professor John Rogers and Professor Yihui Zhang. They microfabricate some of the silicon structure with a very unique geometry, a very large deformation. It's kind of by use the side effect as well as the mechanical design. So that's something. I think this inorganic semiconductor can be used in the flexible electronics, but needs some careful design.
yeah, it's quite tricky.
So, Professor Liu, it's a wonderful talk. You mentioned also the fourth generation semiconductor doping is one challenge. I wonder if we send for mass production, what's the fabrication challenge you would foresee in the near future?
Okay, yeah, you nailed the key point, key question. in order to be mass production and really being used in the industry, we need to address this doping issue. I did not show here. It's some of the very latest results. So one of my postdoc conduct some calculation. We publish in some physics journal. So in fact, with some like deep dopant, with some like a dopant with a deep energy state, by combined strain, we can actually make the deep doping become a shallow doping. So at least from our calculation, we found that through the strain actually can change the doping state, so that make the doping more useful. That's one thing that we're trying to do. Another direction is that we applying a pre-strain, like we pre-strain the semiconductor. Not necessarily such a big strain, like not necessarily like a 9%, but a small strain. And then we calculate the doping energy. And we found that with a certain kind of pre-straining condition, actually we can make the doping easier. So therefore, we indeed explore the doping of the diamond for the future mass production. But we found that actually in the doping, the strain engineering can still be used. They can be coupled. So by combining this strain engineering strategy with the doping, may give some result, some difference. So this may address partly the diamond doping challenge. Yeah, but I know there's other researchers working on some other strategy, like a co-dope, uses multiple elements to dope the diamond. So and some of the researchers use a surface function. I know researcher in Xi'an Jiaotong University and in Japan, they use a surface functionalization to make the diamond become a useful electronics.
Other steps, the fabrication process would be similar to the conventional, like packaging, lithography, or
also there are some difference. There are some difference because the microfabrication diamond in the scale up approach remains in I think not yet mature. Like for example, like the mask used for the diamond it needs some different materials compared to the silicon microfabrication process. So yeah, we do work and discuss with the expert in the microfabrication industry. There's a need to also develop a planar microfabrication process for diamond. Yeah, so there's a need to explore in that direction as well.
Yeah, that's very interesting and promising. Yeah. Thank you very much.
Yeah, thank you.
Okay, with that, because of the time limit, I think we need to finish the discussion session. And thank you, Professor Lu, for the wonderful talk again.
Thank you, Joel, for the chairing. And thank you for all the panelists. Yeah,
Thank you.
Very
Bye-bye.
nice discussion. Yeah.
Okay, and before the end of this talk, I think Professor Lu, here is a certificate. I think Professor Zhang will send you by email. And thank you for your efforts and time to give us this wonderful talk. And
yeah, thank you. I would like to thank Professor Zhang for her kind invitation.
yeah, and also please join us this July for the Davos Summit at Davos, Switzerland, on July the 11th to July the 12th. We're the leading scientists and entrepreneurs will converge to explore some cutting-edge science and technology and ignite some innovative discussion. So please remember to register early to avoid missing this great opportunity. And also for next week, I can talk we will have Professor Bao Huajia from Royal Melbourne Institute of Technology, and she will talk about atoll materials for sustainability. And also, thank you all for joining us for today, and please stay tuned.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
汽车电子化的迅猛发展，正在掀起一场技术革新的浪潮。其万千期待于一身的电子元器件，必须以更高的技术水平和可靠性，为汽车电子化提供支持。多层陶瓷电容器、电感器、高可靠性元器件，太阳诱电挺身而出，肩负起推动未来科技进步的重任。电子元器件的发展与汽车、工业设备和网络时代的发展密切相关。为此，太阳诱电开始了充满激情的挑战。心怀梦想，无畏挫折，不懈奋斗，为用户、为未来高新技术领域倾力打造、倾情奉献优质的电子元器件。太阳诱电将吸引全世界的目光。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第1次 iCANX会。